In this video lecture, I will introduce the concept of fraction of emissive power that lies in the wavelength interval lambda 1 and lambda 2 at a given surface temperature T. So in order to understand this concept, consider a black surface. Let it be a filament of an incandescent lamp at a temperature of 150 degrees Celsius. Let this is the filament. Temperature is 150 degrees Celsius. It will emit radiations with wavelength 0 to infinity. The total emissive power equal to sigma T raised to 4. Now we know that the ordinary light having a wavelength between 0.4 micrometer and 0.8 micrometer, ordinary light. Now we calculate the emissive power of the surface for the ordinary light. We calculate the emissive power for the surface for ordinary light or for radiations having a wavelength between 0.4 micrometer and 0.8 micrometer. We have to calculate the emissive power of the surface for this wavelength to the emissive power for the entire surface, that is sigma T raised to 4, meaning the numerator of this term is emissive power with wavelength 0.4 micrometer and 0.8 micrometer. The denominator represents the emissive power having a wavelength between 0 to infinity. This is equal to sigma T raised to 4. So this is the problem. Now before discussing the details of that, I will introduce few symbols which will be helpful for you. F0 to lambda 1 equal to EB0 lambda 1 divided by sigma T raised to 4. EB0 to lambda 1 means emissive power of a black surface having wavelength 0 to lambda 1 divided by sigma T raised to 4. It means emissive power of the black surface having a wavelength 0 to infinity. This is 0 to infinity. Now this ratio is represented by F0 lambda 1. Similarly, F0 lambda 2 equal to emissive power of the black surface from wavelength 0 to lambda 2 divided by total emissive power of the black surface. So F0 lambda 1 and F0 lambda 2. Now our aim is, what is F of lambda 1 to lambda 2? That means fraction of emissive power with wavelength lambda 1 and lambda 2. Meaning, what is the amount of radiation emitted with wavelength lambda 1 to lambda 2 to sigma T raised to 4, which is the total emissive power. Let the fraction of radiation with lambda 2, that is F of 0 to lambda 2, അതായത് 0 തുടങ്ങി lambda 2 വരെയുള്ള wavelength ഉള്ള റേഡിയേഷൻസിന്റെ ഫ്രാക്ഷൻ എന്ന് പറയുന്നത്, ടോട്ടൽ എമിസീവ് പവർ ആയിട്ടുള്ള ഫ്രാക്ഷൻ എന്ന് പറയുന്നത് ലെറ്റ് ഇറ്റ് ബി 0.8. അതേപോലെ തന്നെ ഫ്രാക്ഷൻ ഓഫ് എമിസീവ് പവർ വിത്ത് wavelength 0 to lambda 1, let it be 0.3. 0 തുടങ്ങി ലാംഡ 2 വരെ വേവ്ലെങ്ത് ഉള്ള റേഡിയേഷനും ടോട്ടൽ റേഡിയേഷനും തമ്മിലുള്ള റേഷ്യോ 0.8. 0 തുടങ്ങി ലാംഡ 1 വരെ വേവ്ലെങ്ത് ഉള്ള റേഡിയേഷനും ടോട്ടൽ എമിഷനും തമ്മിലുള്ള റേഡിയേഷൻ 0.3. അപ്പോൾ ലാംഡ 1 തുടങ്ങി ലാംഡ 2 വരെ വേവ്ലെങ്ത് ഉള്ള റേഡിയേഷൻസിന്റെ ലാംഡ 1 തുടങ്ങി ലാംഡ 2 വരെ വേവ്ലെങ്ത് ഉള്ള റേഡിയേഷൻസിന്റെ ഫ്രാക്ഷൻ എന്ന് പറയുന്നത്, ടോട്ടൽ എമിസീവ് പവർ ആയിട്ടുള്ള ഫ്രാക്ഷൻ എന്ന് പറയുന്നത് എഫ് ഓഫ് 0 to lambda 2 minus f of 0 to lambda 1. That is f of lambda 1 to lambda 2 equal to f of 0 to lambda 2. this is represented like this. EB 0 to lambda 2 divided by sigma t raised to 4 minus f of 0 to lambda 1. Emissive power 0 തുടങ്ങി lambda 1 വരെ ഉള്ളത് divided by total emissive power. So f of lambda 1 to lambda 2 can be written like this. F of 0 lambda 2 minus f of 0 lambda 1. Now another thing is, this fraction is a function of lambda and t. This fraction is also a function of lambda and t. Of course, it contains some constants like sigma, c, etc. Now, if there is a value of lambda t, for that value of lambda t, there is a unique value for this fraction. Similarly, for a value of lambda t, lambda 1t, there is another unique value for this fraction. So if we can form a chart like this, for different values of lambda t, we can plot a chart like this. X-axis is the lambda t. For each value of lambda t, there is a unique value for this fraction. So when you plot the fractional values 0 to lambda, fraction values on the y-axis, you will get a plot like this. That means let lambda equal to say 0.4 and t equal to 1000. Then lambda t equal to 0.4, lambda t equal to 0.4 into 1000, that is 400. That is 400. So if you take lambda t on the x-axis, say 400 micrometer Kelvin here, corresponding to lambda t equal to 400 micrometer Kelvin, you will get a unique value for this fraction. അതായത് 0 തുടങ്ങി 0.4 മൈക്രോമീറ്റർ വരെ വേവ് ലെങ്ത് ഉള്ള റേഡിയേഷനും ടോട്ടൽ റേഡിയേഷനും തമ്മിലുള്ള റേഷ്യോ എന്ന് പറയുന്നതാണ് ഈ y ആക്സിസ്. That can be, you can calculate from the y axis. So for the value of lambda 1t and lambda 2t, you can calculate these values from this curve. So this is lambda 1 and this is f of 0 to lambda 2. So if we want to calculate the fraction of emissive power between lambda 1 and lambda 2, f of lambda 1 to lambda 2 equal to f of 0 to lambda 2 minus f of 0 to lambda 1. The value of f of 0 to lambda 2 and f of 0 to lambda 1 can be taken from the data book. In some data books, this curve is given. In some data books, corresponding to the value of lambda t, the value of f of 0 lambda 1 is given in a tabular form. So we use the data available in the data book in the form of a tabular form. So